Hello and welcome back to Manifolds, the video series where we talk about generalized surfaces and calculus on them. And in today's part 24, we will connect the abstract differential from manifolds to the ordinary differential from multivariable calculus. Hence, today we will see that our calculus on manifolds generalizes what we already know. However, before we start sketching some manifolds, I first want to thank all the nice people who support the channel on Steady, here on YouTube, on Patreon, or by other means. And please don't forget, as a supporter, you can download different PDF versions for this video, and you can also test your knowledge in a quiz. Okay, then without further ado, let's answer the question how the differential looks in local charts. Now, in order to do that, let's take two manifolds M and N again and a smooth map F between them. And then the differential was defined pointwisely, so we have to fix a point P here and the image on the right hand side. And now you should know, by the definition of a manifold, we find an open set around P that is homeomorphic to an open set in Rn. So please don't forget, this is a very important fact. Locally, a manifold of dimension n looks like Rn. So you see, this is the common picture we have. We have a homeomorphism between the manifold and Rn. Or more precisely, H is a homeomorphism between these two open sets. And a similar thing we have on the right hand side with a homeomorphism K. And of course, we could also have a different dimension on the right hand side. So let's say we have Rm. Okay, and now please recall, the map F is smooth if and only if the corresponding map here on the lower level is smooth as well. In other words, here on the lower level, we have an ordinary differentiable map. So this one we call F tilde, and it's a nice map from Rn into Rm. Hence, now we can ask the question, what is the connection of the differential of F with the differential of F tilde? And in order to make everything a little bit simpler, we can bring this H inverse to the other side. So you should remember, K after F is equal to F tilde after H. So in other words, both maps here just represent the arrow from here to there. And now what we can do is to look at the differential of this map there. And for that, let's choose an abstract tangent vector from the tangent space TPM. And then let's put that first into the differential df and then the result into the differential dk. This means here in the inner part we have dfp of our tangent vector. And now I would say this is the perfect time to recall the definition of the differential. Namely, it's simply an abstract tangent vector given by f after gamma. This means here in the equivalence class we now find a curve on the right hand side. Hence, this we can now put into the differential of k. And of course, this does not do much because it also is just a composition again. However, since k maps into the concrete Rm, this abstract tangent vector can be rewritten as a very concrete one. Namely, that's exactly what we have learned in the last video when we talked about submanifolds. This means now the concrete tangent vector can be written as a derivative. Now, this is helpful because now we can substitute our k after f with f tilde after h. And indeed, this is a very nice thing because we already know f tilde is this ordinary map between Rn and Rm. In conclusion, here we can apply our ordinary chain rule for multivariable calculus. In particular, what we can use now is the Jacobian matrix of f tilde, simply because this represents the differential of f tilde. And of course, the point we have here is h of p. And please don't forget, this comes from h of gamma of 0. And now, this Jacobian matrix is multiplied by the differential of h after gamma. And please don't forget, this is also an ordinary map from R into Rn. And the point where we evaluate this differential is given as 0 as before. Okay, so there you see, this is very nice. Now we have introduced the Jacobian matrix of f tilde. Now, therefore this will stay, and the other part here we will translate back to an abstract tangent vector. This means we do the same thing as before. We use the bijection we have between abstract tangent vectors and the concrete ones for submanifolds. And if we rewrite that like this, then we see we can introduce the differential of h. Namely, this is simply the differential of h applied to the tangent vector represented by gamma. And there we have it. This is the whole calculation I wanted to show you, because there we now can bring dh to the other side, or we can bring dk to the right hand side here. And let's do the latter, because this one explains how we can see the differential. So on the one hand, we can say f is given in local charts as k inverse, composed with f tilde, composed with h. And now we know by the calculation I showed you before that df is also given in local charts. Namely, if we just write it in short terms, we have dk inverse composed with the Jacobian matrix of f tilde composed with dh. Of course, the correct version you see here on the right hand side in the calculation, where we also should put the point p to dh. However, I would say this short version here is a good thing to remember the whole acting of the differential. And indeed, it tells us that the differential of this abstract smooth map f is given as the Jacobian matrix in local charts. In other words, now you see that these strange definitions with abstract tangent vectors were the correct way to generalize a differential. Therefore, it makes sense to continue our discussion of the differential in this form. Therefore, I would say let's do that with the next videos. So I really hope I see you there and have a nice day. Bye bye.